This is the video for Unit 7, Lesson 1, Exponential and Logarithm Form. The goal we're going to be looking at is writing an exponential equation or statement in logarithmic form, and to do the reverse of that, so writing a logarithmic equation or statement in exponential form. So when we talk about a log, which is obviously brand new, it ties very closely when we talk about an exponential function. So when we talk about exponential functions, we had our a times b to the x, or if a was 1, it was a b to the x. And we also talked earlier in the school year about inverses, right? So how do we undo an operation? What we're eventually going to see is what do we do when we have something like, let's say, 2 to the x equals 7? How would we go about even solving for x when it's in the exponent? So we need to know how to work with inverses of an exponential, and the way we do that is we use what's called a log. We can also do functions with logs, and there's a lot of other properties that go along with it as well. So logarithmic form, how we read that is this would be read as log base b of x, or log x base b, it can be read both ways, is equal to y. And what that actually means is b is actually the base. Y would be, when we rewrite this, would be like our exponent. And then x is typically what we would have after we evaluated it. So an easy way to rewrite it, I like to use the phrase follow your heart. It makes like a little heart shape. And so we rewrite this as b to the y is equal to x, right? So this is our base, this is our exponent, and this is what it would equal. And it makes like a little heart shape. So if I want to rewrite a log, I can rewrite it in exponential form if that's going to be easier for us to work with, and vice versa. So for example, for this first set, we're just rewriting this in exponential form. So this is log base 3 of 9 is equal to 2, or log 9 base 3 is equal to 2. So if I go ahead and rewrite this, this is the same as saying 3 to the second is equal to 9, which we actually know is already a true statement, right? 3 squared is 9. Same idea when I have a fraction. So if I rewrite this, this is saying 4 to the negative 2 is 1/16, which is accurate, right? So if a negative exponent flips it down, we'll square it, we get 1/16. The two u tries will have u try. And then the reverse of it is the exact same thing. You just have to make sure you remember that you're using a log. So if we're working with exponential form, the inverse of that is a log, and we can rewrite it. So and sometimes that's more helpful to use. So when we go ahead and rewrite this, I'm going to do the same thing, but I have to make sure I write the log first. So log base 14, because that's our base still, of 196 is equal to 2. Same thing with the next one. I'm going to rewrite it. So this would be log of base 1/3 of 9 is equal to negative 2. Or you might say log 9 base 1/3 is equal to negative 2. The two u tries you can try out, but it's the same thing. And then we can use this rewriting if we wanted to evaluate, and we'll eventually learn how to use our calculator, but this is the same thing. So I want to know what log base 5 of 25 is going to be. I'm going to put an x. I don't know what it is, but I could actually, if I want to, I can rewrite it. And this is saying 5 to the x is equal to 25. So this is the same as saying what exponent of 5 will give me 25. You maybe don't even have to rewrite it, but you know 5 squared is 25. So x would have to be 5, or 2. Sorry, 2. And we'll see more of these exponential equations later in the unit. Same idea, if I have like log base 4 of 1, I'm going to write it as, I don't know what it equals, let's say. This is the same as saying 4 to the x is equal to 1. Anything raised to the 0 power is going to be 1, so x we know would be 0. The u tries you can try out, but it's the same thing. You can see if you can rewrite it and find the variable. So we then start to look at what happens if it's not a log that we can rewrite and easily find the value of x. So our calculator, and depending on what type of calculator you might have an updated one, but a lot of calculators can do only really the log and the natural log. And we're going to see that in a moment. So the common log we use is actually, you're going to see it's like a log. It just says log, L-O-G. And really, that's a base of 10. So on our calculator, we're going to see a base of 10 that's secretly there. So in your calculator, you're going to use the log button, and I'll show you that in a moment. So if I wanted to evaluate the log of 42 in my calculator, it's actually doing the log base 10 of 42. So 10 to what power gives me 42? That's how we kind of are thinking of it. So in my calculator, I would actually hit the log button. The log button is actually right next to the 7. And if I was to do log of 42, that would end up giving me my answer. I like to close the parentheses of 1.62, for example. So what does that actually mean? That basically means 10 to the 1.62 power is 42, right? So I found the exponent that would do that. Another button our calculator has that we can frequently use is the natural log. That's written as ln. For natural log, and really that's the same as saying a base of e, which we saw e when we were doing our continuous compound interest. E is an irrational number, so remember we talked about when n increases and it starts to, in that formula, it approximates e, which is about 2.78. In our calculator, we would use the ln button. And so the natural log of 42 is really saying the log of base e of 42. So in my calculator, it would look like I would have natural log, which is next to the 4 key. If I typed in 42, that's saying, let's say I get 3.74. So what that basically means is e to the 3.74 power would give me about 42, right? So it's telling me what that exponent would be if I did the inverse. So really, when nothing's written for a log, we assume it's a 10, and when they write ln, that's going to be a base of e. So we can actually rewrite this now. So if I wanted to have like an expression or an equation, I don't see anything here. It's really like there's an imaginary 10. And if I wanted to convert it, I'm really doing the same thing. So 10 squared is x plus 2, right? Same thing here. If I rewrite this, this is saying if I want to say log base 10 of 92 is x, but I don't even have to write the log there anymore. If it's a base of 10, it's kind of one of those rules we assume there's a 10 there. So it's really saying the log of 92 is equal to x. If it's a natural log, that's the same as an e. So this would be like e to the 5th equals 3x. And then if it's already an e, that's the same as saying the natural log of 24 is x plus 2, right? Because this is the same as saying log base e of 24. And instead of that, we can just write the natural log. The last examples we're going to see is just simply getting comfortable using these in our calculator. I like to use parentheses just so you know what part's getting evaluated by the log. So when we rewrite this, let's say I'm going to do, and it says nearest thousandth, that's 3 decimal places. And so if I'm going to do the log of, I'm going to clear this out. If I do the log of 5, I'm going to do log 5. And you don't have to close the parenthesis, but I like to. And if I round 3 decimal places, I actually have that to be 0.699. If I do the log of 27 plus 1, notice the parentheses around the 27. So the log is only evaluating the 27. It's like it's taking the answer and putting a 1 there. So we have the log of 27, close the parentheses, plus 1, and we would get 2.431. For the next one, we're going to see some when we talk about properties, what happens with this next one. But if I do the natural log, which I don't need second, if I do the natural log of e, put a 1 here, we actually end up getting 1, and then I would add a 1 to that, and you would get 2. So whenever I take a log, a base b of that same value, you're always going to get 1, right? Because it makes sense. E to the 1 is going to give you e. So this always is going to come out to be a 1. And then the last one you're going to see is if we do the log of -5, you actually get no solution, right? Because if you think about it, it actually makes sense. If I have a base 10, 10 to what power is going to give me -5? There's no such power that's ever going to make that into a negative, right? Because it's an exponential function. So you're going to find for logs that whenever, when we evaluate, there's going to be no negatives that we're going to have, or whatever value is inside here has to be greater than 0. Otherwise, you're going to get a no solution, right? Because our exponentials, remember, unless there's like some sort of translation, is never going to dip below that y equals 0. So if you have any questions, you could feel free to ask in class, sign up for T-Bolt time, or go to the center.